Hi there, my name is Mike Markus. I'm the General Manager of the Orange County Water District. And today we're going to give you a tour of the Groundwater Replenishment System. Now this project produces 100 million gallons per day of recycled water, and it's the world's largest potable reuse project. Before we start the tour, let me talk a little bit about the Orange County Water District and what it is that we actually do. We manage a very large groundwater basin in central and northern Orange County. We provide 77% of the total water demands for 19 retail water agencies. So we're a very important source of supply of water into Orange County. Now that's important because here in Southern California we get very little rainfall, about 14 inches a year. And we rely predominantly on what we call imported water, which is water that's brought from either Northern California or the Colorado River. So this imported water costs more than groundwater. So for our retail water agencies, it makes a lot more sense for them to be able to pump as much groundwater as they can because it's less expensive. So in order to do that, because we lack the supply of water because it's so dry, we have to rely on local sources of supply. And that's what recycled water gives us. So with this project, the Groundwater Replenishment System, we're able to provide 103,000 acre feet per year, or about enough water for 850,000 people, which is extremely significant. Now we can't do that without our partners next door, the Orange County Sanitation District. So the Orange County Sanitation District provides the industrial and municipal treatment of wastewater. They purify the wastewater to secondary effluent. That secondary effluent then is clean enough to be able to discharge into the Pacific Ocean. But instead of discharging it into the ocean, they divert that secondary effluent to the water district, and we run it through an advanced purification process. This advanced purification process consists of microfiltration, reverse osmosis, and UV light with hydrogen peroxide. By the time that secondary effluent has been gone through this advanced treatment process, it's of near distilled water quality. We then take that water, we put it back into the groundwater basin, so it becomes a source of supply to the basin, and then those retailers over time pump that water out of the ground and serve it directly to our customers. So it's a very unique project. It's one that's being replicated around the world, and we'd love to give you a tour of it today. We're going to start out, we're going to look at the three major processes. So we're going to start with the microfiltration, and then we'll move to the reverse osmosis, and then finally the UV light with hydrogen peroxide. So let's get started. Let's go over and take a look at the microfiltration. The first step of the process is microfiltration. And microfiltration removes any bacteria, protozoa, or suspended solids out of the water. Now we can see right down below us here what I call one cell of microfiltration. Now this cell of microfiltration will actually purify 2.5 million gallons of water per day. This is an actual membrane module. So this membrane module contains the membranes. And inside this plastic casing, there's around 15,000 individual fibers and polypropylene fibers. And this is the actual membrane. Now what happens is water is continually fed into the microfiltration cell, and there's some pumps in the basement that pull the water through the membrane. Now this membrane is a hollow fiber, or a straw. So consider this a straw. Now this straw has tiny holes also in the side of it that are 0.2 microns, or 1/300th the size of a human hair. So what's happening is the pumps are drawing a suction. So if I pinch the bottom of this straw, put it in water, and then sucked on the straw, the water would come through the sides, through those tiny holes, and then out the top. Anything larger than 0.2 microns would stay on the outside of the straw. And that very simply is how microfiltration works. However, you can imagine as you continue to draw suction on the straw, those solids would accumulate on the outside of the straw, and it would take more suction to bring the water through the straw. So every 21 minutes, each one of these cells goes through a backwash or an air scour. So we actually inject air into the basin. It stirs up the contents of the cell, knocks the particulate matter off the membranes, and that particulate matter is put into suspension. And then after about a minute of the air scour, the contents of the tank drain, and that water then goes back over to the sanitation district. We then refill the basin, and then it continues to filter until another 21 minutes are up, and then it goes to the backwash. So each one of these 36 cells in the microfiltration area are going through a backwash every 21 minutes. Now, over time, we do get a bit of biological fouling on these membranes. So every 21 days, each one of these cells is soaked in a solution of citric acid and sodium hydroxide, an acid and a base. And it goes through a chemical cleaning. And after that chemical cleaning, the biological foulant is destroyed. And then we put the cell back into operation, and it continues operating at a very high rate. Now, as long as we continue to backwash every 21 minutes and clean each cell every 21 days, these membrane modules will last for about 7 years, and then we have to replace them. So this continual process, as I said, is the first step in the process. It's an excellent pre-treatment for the reverse osmosis. So now we're going to head over, we'll actually head down into the basement first and take a look at the microfiltration. And then we'll head over to the reverse osmosis and then the UV. So why don't you follow me and we'll go downstairs and take a look at what we can find. And now we've come downstairs into the microfiltration basement. And you can see all of these pumps and all of the piping. This is where all the piping and the pumps are for the microfiltration process. So if you'll follow me, we'll get a little closer look. So now we're in the basement, the microfiltration basement. And a few minutes ago, we were standing about 25 feet above where we are now. And we were looking over into the microfiltration cell. On the other side of this concrete wall is where those microfiltration cells are. In the basement here is where the piping is. So this is where the water is brought over from the Orange County Sanitation District into the microfiltration area. So this large blue pipe is bringing the secondary effluent from the sanitation district. This is a lug wafer butterfly valve. This valve is normally open. The one on the bottom normally closed. So the water will continuously flow into the adjacent cell. And it'll continue to do that until it requires a backwash or an air scour. At that time, the process control system will tell this valve to close and this valve to close. And then at the far end of the where we are standing right now, there are the blowers. The blowers will turn on. The air scour will begin. That'll last for about a minute. After a minute, the bottom valve will automatically open, and then the water will flow from inside the cell down into an underground pipe that takes it over to a waste sump, where it's then pumped back to the Orange County Sanitation District. So all the microfiltration waste goes back to the sanitation district and actually runs through their secondary process again, and then comes back to us and we treat it again. So after that, this valve will close, this valve will open, and it will continually then to feed the system. As you can see, all the piping around us is identical. Each cell has its own individual piping system, which is very important because it allows us to take just one cell. If something goes wrong with this actuator or this valve, we can take this one cell out of operation and continue to operate the remaining microfiltration cells. So that's a very important design consideration, I feel. The other thing is we use pneumatic actuation. We use air to open and close these valves. So all of these valves are air controlled. What that allows us to do is automatically open and almost instantaneously close the valves. If we were to use an electric motor operator to run these valves, what would happen is take 30 to 90 seconds to open or close the valve, and we'd lose a tremendous amount of efficiency in the plant. So there again, when we designed the plant, we looked at ways to optimize the efficiency, the operational efficiency of the plant. So now let's go on the other side and take a look at where the water comes out. So now we're on the other side of the microfiltration cell. So what I just got done showing you was where the water goes into the cell. On this side now is where the water gets pulled out. So we have this pump right here, which is a horizontal centrifugal pump, 60 horsepower motor, and this provides the suction to pull the water through the membranes. So this valve will draw the suction through that large header on the top. It'll pull the water out of the 684 membrane modules on the other side of the wall in a cell and pull the water through. The water then comes through the pump, goes up through the valve, flow meter, up into the big blue pipe on top, and then all of that water goes down and goes through the 84-inch blue line on the far end of this aisle. So what's happening here is we're taking in a lot of data. We're measuring pressure, we're measuring temperature, we're measuring water levels on the inside, we're measuring flow. All of this information being gathered through the process control system. And then the process control system telling valves when to open, pumps when to start, what the sequence needs to be throughout the entire process system. So remember, we have 36 cells of microfiltration, and if you walk through this basement, you'll see this same piping scheme replicated 36 times, as you will on the other side with where the water goes in. So there again, it gives us a high degree of reliability throughout the system. It allows us to very much optimize the efficiency and the treatment of the water. So let's now walk on and go to we'll head towards the RO building. So now we're in the reverse osmosis building, or RO as it's commonly known. And RO is really the workhorse of the treatment process. So through this process, we remove any dissolved minerals, viruses, or pharmaceuticals that may be in the water. In fact, the only thing that gets through the reverse osmosis are very, very small, low-weight organic molecules, and the next step takes care of that. But what we have in front of us is what we call 1 unit of RO. This 1 unit will actually treat or purify 5 million gallons per day. So currently we have a total of 21 units throughout this building. So normally 20 of those would be operating and 1 would be on standby. So the 20 operational units would be able to produce the 100 million gallons per day. Now this unit that we're looking at consists of 150 pressure vessels. So these white fiberglass long tubes are called pressure vessels. And inside each one of these tubes is the actual RO element. And there's 7 RO elements in each pressure vessel. And we have an actual RO element. So this is an actual RO element. They're 8 inches in diameter, 40 inches in length. And as I mentioned before, there are 7 of these that are in each pressure vessel. They're all lined up in series, one by one. And those contain the actual membrane. So what this process does is through high pressure, we're pushing water through this membrane. And the membranes we use are thin film composite polyamide membranes, so really state-of-the-art membranes. They operate at much lower pressures than the type of membrane that we used before, the cellulose acetate membrane. So these will operate anywhere between 150 and 200 psi. And in order to force the water through the membrane, each RO unit has its own individual high-pressure RO feed pump. So this is the RO feed pump that supplies the pressure for the unit that we were looking at. And this vertical turbine pump will provide that pressure up to about 200, 250 psi, enough force to force the water through these pressure vessels and elements. Now the type of RO that we use is called a single pass 3-stage process. So what that means is all the water goes through the first 78 vessels. And as it goes through, we're squeezing the pure water out of it So as the water goes down and through this pressure vessel, it's getting more concentrated. It then goes through the next 48 vessels. There again, continually squeezing the fresh water out, the water becoming more concentrated as it goes through. And then the final stage goes through the last 24 pressure vessels. And by that time, the water is fairly high concentrated. We've squeezed just about all the water we can out of it. We get about 85% recovery through this process. So 85% of the water that comes in comes out as purified water. The other 15% is that concentrate, or brine as it's sometimes referred to also. Now that brine or concentrate goes back to the sanitation district, and then it goes back into their ocean outfall and is discharged to the ocean. So there's no treatment of the brine flow. So that concludes the RO portion, and now we're going to go right outside the building and look at the final step of the process, which is ultraviolet light and hydrogen peroxide, better known as UV-AOP. So now we're at the last step of the treatment process. And as I mentioned before, we do get some low-weight molecular organics that do get through the reverse osmosis. So that's why we have this final step, which we call UV light with hydrogen peroxide. So the water that's treated out of the reverse osmosis comes from the RO, and then it comes into these vessels. And the water comes in through this first vessel, goes across it, up into the second vessel, up to the top, over, and then out. Now during this process, we're exposing the water to high-intensity UV light. And in fact, in each one of these vessels, there's a total of 144 UV lamps. So if I were to open up, pop off this cover, be able to take a look, I'd be able to see inside. And what I'd see is something like this. I'd see an actual UV lamp, and this is the lamp right here. It's in a quartz sleeve, so the lamp is not exposed to the water. The water flows over these quartz sleeves. The UV lamp is what's providing the intense UV light, and it's that UV light that is actually destroying some certain compounds. So we have to test for a certain compound called NDMA, N-NITROSODIMETHYLAMINE. And we have to test this or remove it to below 10 parts per trillion. And UV light will do that. What happens is the photons of light that are generated from the lamp will actually break the chemical bonds of the compound and render it neutral. So the NDMA is destroyed through the UV light. So there are certain compounds where the UV light has no effect on that compound. One of those being 1,4-dioxane. So the manner in which we remove the 1,4-dioxane is a little bit different. What we do is we add hydrogen peroxide upstream or before the UV light. That hydrogen peroxide, or H2O2, through direct photolysis is actually transformed into a hydroxyl radical, an OH dot. So that hydroxyl radical will then chemically combine with the 1,4-dioxane and render it into a neutral compound. So what's really great is we actually have two things going on in this process. We have the direct photolysis, and we also have what's called advanced oxidation. And so through that process, we're destroying different types of compounds. And utilizing this multi-step membrane process that we've gone through, the microfiltration, followed by the reverse osmosis, followed by the UV light with hydrogen peroxide, it's the best available technology, fully endorsed by the regulators, and it works. We've been running this plant for a little over 12 years, and to date, we have never been in a non-compliant situation when it comes to our permit. So we know the process works, and we have to test for over 400 different compounds as a part of our permit. And once again, never had an exceedance of those permit conditions. So the process works, it's being replicated around the world, and we're just proud to have been able to kind of pioneer this effort and bring it forth so that others could learn from us and develop their projects as well. So now the final thing, we've got to taste the water. So follow me over to the sample sink. So now we're at the sample sinks. And we use this as an educational tool for people to come through and join us on the tour. And hopefully one of these days you'll be able to come here in person and enjoy firsthand an actual tour with our great staff. But in these sample sinks, the middle sink is meant to represent the water that's coming out of the microfiltration and going into the reverse osmosis. So that water is coming into the RO, and then the RO is squeezing that water into purified water and also concentrate, which is in the far right sink. So you can see the discoloration there. The concentrate is darker, whereas the purified water is perfectly clear. So when we come to the end of the tour, we go to the sinks, we explain the sinks. There's only one last thing to do, and that's to taste the water. So this is the water that's been through the entire treatment process. Now the one amazing fact, at least amazing to me, is it only takes about 45 minutes from start to finish. So when we were just starting our tour, this water was probably in one of those microfiltration cells, and it's already come through the process. We now have water that is near distilled quality, and we'll give it a taste. And that water really tastes good. And what people ask me after a tour, they'll say, well, Mike, it tastes like water. And we say, well, it tastes like water because it is water. So we hope you've enjoyed the tour. As I mentioned before, if you have a chance, you're in Fountain Valley, Southern California, I encourage you to please stop by. We offer specific tours for specific groups if you so wish. So stop by so that we can show you this facility, and I'm sure you'll enjoy it. Thanks for your time.